In this video, we're going to go over the 4 laws of thermodynamics, and we're going to start with the 0th law. This law deals with basically temperature, the definition of temperature. It's a pretty simple idea. Let's say I have 2 objects at different temperatures. We'll call this one over here TH because the temperature is hot, and we're going to call this object over here T cold, because the temperature of this one's colder. So we know that T hot, temperature hot, is greater than temperature cold. The 0th law simply says that energy is going to flow from an object at higher temperature to an object at lower temperature if, they're in thermal contact with one another until the temperatures are equal. That's it. And then at that point, we'll call it T medium. The net energy flow stops. It's a simple idea. And once the temperatures equal one another, the 2 objects are said to be at thermodynamic equilibrium. Now let's move on to the 1st law of thermodynamics. This law you've heard of before. We covered this a lot this year. This law says energy cannot be created or destroyed. Another way of talking about this law is the amount of energy we have in the universe is the amount of energy we have in the universe. Now this refers to the universe. So remember, your universe is going to be equal to your system plus the surroundings. So what this means is that if something is losing energy, say your system's losing energy, so the system loses energy, that energy is going to have to go somewhere. The surroundings are going to have to gain energy, and vice versa, right? If the surroundings lose energy, then the system's going to have to gain it. That's basically the idea. Now, the universe itself can't lose energy, but that does not preclude the system from losing energy, and it does not preclude the surroundings from losing energy. It just means that, like I said, if the surroundings lose energy, the system has to gain it. If the system loses energy, the surroundings have to gain it. Pretty simple idea. Now we're going to move to an idea that's a little more difficult. This is the 2nd law of thermodynamics, and I hear people get this wrong all the time. The 2nd law of thermodynamics deals with entropy, but a specific type of entropy. It says that the entropy of the universe is always increasing. Notice, this is the universe, okay? And we're going to remember, the universe is the system plus the surroundings. All right, let's look at this in a little more detail. Notice it says the universe is always has an entropy that goes up from one moment to the next. Now that doesn't mean, for example, that a system under study, that doesn't mean a system can't drop in entropy. I mean, this happens right here. Let's look at this. H2O liquid going to H2O solid. This represents a system that's undergoing a drop in entropy. So let's just say, let's just say it goes down in 10 joules per mole Kelvin during this process. I can't remember what it is, but just for the sake of argument, we're going to say during this process, there's a change of negative 10 joules per mole Kelvin. What that tells me then is if the system drops 10 joules per mole Kelvin, then the surroundings is going to have to at least gain 10 joules per mole Kelvin, and it's going to be a little more than that, so we'll just make it 10.1. So in this case, the universe would have a total change of 0.1 positive joules per mole Kelvin. So notice, there are things in the universe that can undergo decreases in entropy, as long as, during the decrease in entropy, the surroundings more than make up for that decrease. That's what the 2nd law of thermodynamics deals with. Finally, we'll go to the 3rd law of thermodynamics. This law also deals with the entropy, and it states the entropy of a pure crystal at absolute zero is zero. So you have perfect organization, I suppose. Your crystal is perfectly arranged, and it's not vibrating at all because there's no thermal energy to this thing whatsoever. As soon as you start to raise the temperature of this, the entropy is going to start going up. And this we've covered this. This is the idea that substances increases in entropy as they go from solid to liquid to gas. I'd like to go back to the second law of thermodynamics and relate it to a familiar equation to you. So first, we're going to understand that the second law says that the change in the entropy of the universe is always going to be increasing. So it's always going to be greater than or equal to zero. It's going to be a positive value. The entropy of the universe always increases. The universe consists of both the system, which is the chemical equation under study, and everything else that surrounds it. So the entropy change of the universe will be the entropy change of the system and the entropy change of the surroundings. Now, what would be interesting is if we could relate the change in entropy of the universe to a chemical system. So we only have to focus on the system and figure out whether that system is going to be spontaneous or not. And it would be spontaneous if this ends up being true, because it's going to follow the second law. Well, that'd be interesting if we could have an equation that helped us do that. So let's just take this particular reaction here, H2O liquid going to H2O solid, just for the heck of it. And we know there's an enthalpy change that's associated with this. So when liquid water freezes, that's actually exothermic. So there's a delta H for this particular system. And we should recognize that the enthalpy change in the system is going to be the opposite of the enthalpy change in the surroundings, correct? Because if the system loses enthalpy, the surroundings they're going to gain it. So let's make a substitution here. Now what's interesting is there's an equation that relates the entropy to the enthalpy in the following way. So the change in entropy of the surroundings, that actually ends up being equal to the change in enthalpy of the surroundings divided by T. So that allows us to make a substitution here. I can actually take the delta H of the surroundings over T, and I can plug it in here. So let's do this right here. The change in entropy of the universe, that should be the change in entropy of the system. Let's see, add the enthalpy change of the surroundings, which I'm going to write as delta H surroundings over T, like that. But we notice here that the change in entropy of the system is the opposite of the enthalpy change in the surroundings. So I can put this whole side of the equation in terms of the system in the following way. I can say the change in entropy of the universe, that's going to be equal to the change in entropy of the system minus, that's going to be what? The opposite of the delta H of the system over T. That's pretty cool. And now what I'm going to do is I'm going to multiply everything here by temperature. So if I do that, I get T delta S of the universe. That's going to be T delta S of the system. Well, if I multiply this by T, they cancel. Minus delta H of the system. You might see where this is going. Now I'm going to multiply everything by a negative sign. So I get negative T delta S of the universe. That's going to equal, well, this will be positive and this will become negative, delta H of the system minus T delta S of the system. And this is actually defined here. This term here is actually defined by Gibbs as the free energy. So delta G is delta H of the system minus T delta S of the system. Now we know that this, from the the second law, we know that in order to be spontaneous, the change in entropy of the universe has to be positive. So let's see what these implications have here. So this needs to be positive in order for the system, in order for the change. So this needs to be positive in order for the process to be spontaneous. So let's see, my delta G, oh look at that, a positive times a negative, that ends up being a negative delta G, doesn't it? Now look, I want to make sure I get this straight here. So notice that for delta G, if delta S for the universe is positive and T is negative, that's going to make delta G negative overall. So we see that delta G negative overall corresponds to a spontaneous process. And that fits what we've learned about this particular equation. That delta G is spontaneous if delta H system minus T delta S of the system, which refers to the chemical equation, is negative. On the other hand, if the entropy of the universe ends up going down, which the second law tells us cannot happen, then both this negative sign and delta S of the universe ends up being negative. So overall, your delta G is positive, and in that case, it is going to be a non-spontaneous process. So this particular equation, delta G is delta H of the system minus T delta S of the system. This actually arises from the second law. And it tells us that there are processes that decrease in entropy. Certain processes can decrease in entropy, like, the formation of a snowflake. That represents the formation of something that is very improbable. Nice, beautiful, six-sided structure. That can happen, let's see, as long as it's an exothermic process, as long as this ends up being negative enough that delta G ends up being negative. And indeed, we do know that the freezing of water is an exothermic process, so this can happen. We can get, the formation of beautiful six-sided snowflakes spontaneously, as long as the temperature conditions are correct. And we've covered that quite a bit in previous chapters, and we've covered that quite a bit in a previous part of this chapter.